Now let's use the existence and uniqueness overview and try to navigate questions about uniqueness and existence and uniqueness. So first thing, if we remember, we should look at we have all these questions that are IVP, they're initial value problems, and we want to figure out which one has a unique solution, which one doesn't have a unique solution in a neighborhood. So if I follow that overview, I'm going to look at this one first because that's the one that is a linear differential equation. Like, look, there's a term with only y, and there's only the term with y prime, and then the last term doesn't have any y or y prime. So what I'm going to do is because I know that let's write this in terms of standard format, and then what is p of x? P of x is negative x, and g of x is x squared. They are both continuous at and around x equal to 0. So there is a neighborhood. So what is that neighborhood? Because no matter what I plug in, they're going to be continuous. The neighborhood is really negative infinity and infinity. And that contains x equal to 0. So the IVP has a unique solution. Now we want to figure out, there are a couple that are separable, naming this one and this one are separable. Anyway, we have to kind of figure out f, and we have to find partial of f because they're not linear. None of these three are linear. So what I need to do is start with finding, so if this partial f is x y to power 1/5, then partial of f respect to y is going to be equal to 1/5 of x y to power 4/5, negative 4/5. And it's the same thing here. F is going to be x y to power 1/5, and partial of f with respect to y is 1/5 x y to power minus 4/5. So the question is, first for this part, if I plug in 0 and 1 for x and y in these two functions, f and f sub y are both continuous at 0 and 1, right? So because they are elementary functions. Then I need to know if they are continuous in a neighborhood. Honestly, if I stay away from y equal to 0, I should be fine, right? Because otherwise, everywhere else, the two functions are defined and therefore continuous in this case. Elementary functions again. So I can say that for a neighborhood like for x doesn't matter. So r times, let's exclude 0. And remember, I want the y value here to be in the when we're saying the rectangular neighborhood, we want that y value to be in there. So because y not equal to 0 means negative infinity and zero, union zero and infinity, I'm going to choose the one that contains one for the initial value. So this is the both of those on this rectangular neighborhood, both f and f sub y are continuous, and 0 and 1 belongs to the neighborhood. So a unique solution exists. In the next part, I noticed that notice that f sub y is not defined, hence not continuous, at 0 and 0. So we cannot use the theorem, or theorem doesn't guarantee anything, or it does not anything. Again, is there really a second solution in this case? So what I'm going to do is I'm going to basically take my own advice. These two were selected to be done second because they are basically separable equations, and I'm going to try to see what would a second solution look like if it's an equilibrium. So what is the equilibrium here? Equilibrium solution is y equal to 0, right? If I set that equal to 0 and solve for y as if x was a constant, I get a y equal to 0. And this actually includes the point, the initial point 0 and 0. So this is a second solution if the first solution is different, according to what we had before. And so how do I know if the first solution is different? We basically need to solve the differential equation at the initial value problem through its general solution. So here I can separate these and write dy over y to power 1/5 is equal to x dx, and then solve again by integrating to get y to power 4/5 times 5/4 equal to x squared divided by 2 plus c. Plug in the initial value, and c is going to be 0. So 5/4 y to power 4/5 equal to x squared divided by 2 is the first solution that you found, and then y equal to 0 is a second solution that goes through 0 and 0. So this is how we find a second solution. It turns out that this has many solutions, infinitely many solutions, but this is all that we're interested in so far. So the next part is this one. This is not a separable equation. All I need to do is to figure out if this is the theorem works on this. And so f is x times y minus x to power 1/5, and f sub y is going to be equal to x times 1/5 times y minus x to the power negative 4/5 times derivative of inside, which is 1. Then if I plug in f sub y of 1 and 1, because there's a negative 4/5, just like the ones before, does not exist. So f sub y is not continuous at 1 and 1. And theorem does not guarantee uniqueness.